It's time to get started, huh? All right. So hello, everybody. My name is Brent Roskis. I'm here with my colleague Jaromir. I'm a consulting architect from Red Hat, currently in our global telco practice team. We're here today to talk a little bit about designing NFV architecture at the edge. And unfortunately, there's been a little bit of a change in plan. We had originally put this together with one of our customers, and at the last minute, real world events kind of kept him from being able to participate. So it's just us. And what we've had to do is modify the material a little bit to make sure that it was general purpose information rather than customer specific, because we don't have permission necessarily to use that material. That was going to be presented by our other counterpart. So that's why there's only 2 names on the list right now, but we still have some good material for you, and we hope you enjoy it. So with that, let's get started. All right. So we're going to talk a little bit about network function virtualization infrastructure, NFVi, architecture, and how it can be complicated. And with that, I'll turn it over to Jaromir.
Thank you, Brent. Hello, everyone. My name is Jaromir. I am a product manager at Red Hat for edge computing. And what we will do at this session, we will go a little bit through requirements and challenges, motivation around edge computing, a little bit specific, not really specific to the industry, but overall in general. And then we will deep dive into what are the deployment configurations and considerations. We'll deep dive into one of those, and Brent will walk us through technical challenges, best practices, and other things when deploying into the NFVi infrastructures. We'll end up with what the next steps are in the upstream community development, and close up with some questions if you have. So edge computing motivation, you probably hear it very often. There are many motivators, there are many drivers, what is driving edge computing. In the telco space, it's mostly 5G, but there are also other industries which are driving the requirements. Definitely one of the main drivers is latency. If we want to provide 5G and real-time or close to real-time experience to our users and customers, we definitely need to overcome these physical barriers which we are facing. If we are having centralized data centers, we cannot reach out far to our customers to provide them this real-time experience, because there is definitely some distance between us and between the end user. So we are trying to reduce the latency to minimum. So therefore, we need to deploy the applications as close to the user or as close to the data source as possible. Second one is bandwidth. Again, if we talk about 5G and the amount of end users and the amount of devices which are connecting to the network, we are talking about millions of those devices, and all of those are producing some data, they are sending some requests, and it is very difficult to process all of those requests in one centralized location. Even if it is a huge location, it is not the best practice and it is not really achievable. Therefore, we need to distribute the compute power as close again to the data source or as close to the user as possible, and distribute the responsibilities of the computing. Resilience is another thing in the traditional world and in the traditional data center computing. We are relying on one single data center which might have high availability, might have some plan A, plan B, plan C, disaster recovery options. But what happens if one of those goes down? You definitely can experience some of the service disruptions. If you distribute, again, the responsibilities, and if you make those sites resilient enough, and if one of those goes down, depending on the resiliency level, there might be resiliency at the application level, resiliency at the infrastructure level, you can really reduce the impact to your business and to the service which you are providing to the customer to minimum. Last, which not necessarily applies to the 5G, but might apply to other areas of the industries, is regulations like healthcare or public sector for edge computing, when some of the data might be very sensitive, and there might be some regulations which are preventing you from moving those data between countries or between regions. Therefore, you need to process or store that data at that certain location. Therefore, again, you cannot centralize everything in your single data center, but you need to distribute the computing power closer to where the data is being either processed or generated. As for the challenges, when I was discussing the motivation and the drivers, the challenges are coming with that. When we start talking about the edge computing, one of the main challenges is scale. We are talking about large numbers of the end users, of the devices which are consuming the services. We are talking about hundreds of thousands of sites which need to be collaborating together. Imagine in the 5G world, you have antennas all over your country, and you need to provide your service provider edge close to the antenna. You can be aggregating some of the data, which means you can be closer, but you can have one single device or a couple of devices, a couple of compute nodes which are processing and providing the services to the antenna right at that site. And we are talking then about hundreds of thousands of sites depending on the region. So scale is one of the big factors. When we talk about scale, we also talk about the expertise. In this large scale, you cannot have an IT expert who is going on site and operating that site. You need to have as low impact on operation and as low demand for your IT operations as possible. Therefore, you need to have zero-touch provisioning. You need to have as much automation as possible. You need to have as much of the intelligence built in for self-recovery and other things as possible. So therefore, you need to decrease the requirements for expertise and increase the amount of automation. Last but not least of the challenges is environmental challenges. Again, talking about the deployments of close to the antenna or at the antenna site, there are definitely restrictions of the size of where you are deploying, the location size. So it is highly costly if you need to be designing or renting space which is big enough to satisfy bigger data center. If you are deploying to multiple locations, you don't want to be deploying multiple huge data centers, but really small devices. If you are deploying to some of the locations, and this is outside of the 5G or telco space, but let's say more industrial or more enterprise use case, gas stations, and you are somewhere in the desert, you might have temperature challenges, you might have more security challenges that somebody can easily break into the location and steal those devices. You can have many other challenges which are coming from the environmental space. All of that is underlined with cost. If you are distributing, you're trying also to decrease the cost because you are distributing to large scale. And you cannot afford to have every single site to be costly for you, because then you are multiplying and it is actually becoming exponential growth of your apex. So all of that are the challenges which need to be accounted when we are designing and defining the edge computing architecture, also especially in the terms of NFVi. The NFVi itself brings also a lot of networking challenges and considerations, and Brent will be covering a little bit more in the technological requirements, how to address those. When we talk about edge, we cannot talk about or very clearly specify what the edge tiers look like. It is really a continuum. It is very broad how enterprises, how telcos, or how overall customers are deploying their infrastructure and how far they are from their core or what the latency is between those sites. So it is difficult to standardize that. In the upstream communities, there are efforts to standardize it. However, what we see in the field, it really varies. So this is just a high level, how it might look like, going from the right side, from the far edge, to the left side, to the core. The core being the centralized location where you're aggregating the data, where you're processing the data and disseminating the information to your edge locations. In the middle being the service provider edge, where we are referring and focusing our talk about the NFVi architecture. And the far edge being the end user premise edge, which can be considered either enterprise edge, which is consuming the service provider edge, or which can be the end user device. So when we focus on the NFVi architecture deployments, we can look into two different deployment configurations considerations. First one is to have distributed nodes. Second one is to have standalone clusters at the edge. Both of them have their pluses and minuses. The standalone clusters are referring to the concept where you're deploying multiple clusters, each cluster being at each edge site. So each site has its own standalone resilient cluster with control plane, compute, storage. Really, it is completely self-sufficient. The benefits are fairly clear. It is full isolation. So if something happens between the edge site and between the core location or primary site, it is actually having very low impact depending how you're designing or what dependencies you have. Those dependencies are usually very low. You have high redundancy and you have high availability of that cluster. The complications are that you need bigger hardware footprint because you definitely need to satisfy the needs for control plane at that location. And also that you are introducing more complexity into how those environments are being managed, because then you have hundreds, thousands, tens of thousands, hundreds of thousands of smaller deployments, and you need to manage their versioning, if some of them drift, how you are managing those drifts, and other things. So the complexity of managing and operations of those environments is increasing. Distributed compute nodes is a concept where you have one single cluster deployment. You have primary site, which is having shared control plane. The shared control plane is serving the edge locations. And each edge location, each remote site, has its own resource nodes only. Those resource nodes can be compute nodes, or those resource nodes can be also some storage nodes. Or it can be combined. The benefits are that you are actually reducing the footprint requirements. Therefore, you have a smaller footprint. You have just the resource nodes needs. So if you don't need to deploy 3 nodes for a control plane, if we are taking in consideration HA, you can deploy only 1 or 2 compute nodes and you are done. It is actually faster and easier to scale because you already have all the configuration in place. So what you are doing, you are basically just scaling your resource nodes and deploying your resource nodes without need to standing up the whole cluster. And overall, easier operational management, it is in terms of what I discussed before, configuration and management of versioning, drifts, and other things. This is easier because all your compute nodes are very likely at the same configuration. Complications are coming in terms of resiliency. The control plane itself is single point of failure, so it faces similar challenges when you have your core data center, one single cluster. If something happens to that core control plane, your cluster is going down. It is the same case if you, for example, lose network between your remote site and primary site, core site. You don't have communication between the compute node and control plane. What happens at that point is a few things, depending how your application is designed. It is up and running. It can be accessible from the outside, but it cannot be managed. You cannot really manage your workloads. You cannot deploy VM. You cannot shut down VM. You cannot do anything in terms of OpenStack control plane. So what we will do in this presentation, we'll focus on the distributed compute nodes. So the distributed compute nodes, when we worked with our customers and when we worked with, looked into the upstream community of edge computing with OpenStack, we looked at the patterns and we provided the reference architecture. We have our official Red Hat OpenStack platform documentation available how to deploy this architecture. It is following the distributed compute nodes model, which I discussed previously, and a few highlights about this architecture. It is fully supported by Red Hat, so really when it comes into deploying it, we are using our Red Hat OpenStack Platform 13. which is based on Queens, OpenStack Upstream Queens. It is a reference architecture, so there is really no secret code. There is really no special features or projects enabling that. We are using our standard deployment, but what we did is we enabled it for the edge deployments. So therefore, we designed the reference architecture, configurations, and we tested it. We documented it. We published our testing results, and this is what we came up with. It is cross-industry. It is heavily driven by telco, but it is also applied in other industries. As I discussed some of the use cases, it can be used in other industries, and we are seeing some of the use there as well. Highlights of the solution is for the deployment tool, we are using OOO. Downstream name is Director. The edge resource side is only compute. It does not really have any storage, persistent storage at the edge, and we will discuss a little bit more details later. What you can do in the terms of storage, you can use local ephemeral storage at the local disk, but really no persistent storage per se. The networking model is fairly flexible, but what we are suggesting and what we are seeing in the production is L3 routed networks. The maximum network latency when we were testing it was 100 milliseconds round trip, which was very easily supportable. It does not mean that over 100 the deployment breaks, but the more errors are being introduced into the solution. The network dropouts, as I mentioned, once you lose the connection between the primary side and between the edge side, the workloads are up and running, so it is the best effort. Once the connection gets established back, the compute node reconnects automatically, and the whole environment continues as it was. And last, image sizing is that there are really no limits. Before in the upstream community, we had some limitations on 1 or 2 gigs of images being able to be deployed at the edge sites. This limit disappeared, so really it depends on your bandwidth. And then you can even deploy 50 gig image if you are using raw data and other things. With that, I'll give it to Brent, and he will walk you through the technical considerations and best practices.
Thank you. All right, so now we're going to drill down a little bit on what it looks like, right? Talk about the reference architecture in a little bit more detail. As you can see, we're showing where we have a primary site, and that's where our deployment engine, our undercloud lives. Our controllers are there. We talked about that a little bit. And you can have compute nodes at that site too. It depends on your model, what you need, what you don't need. And you can also have volume-backed sender storage at that site. And you can use that at the central site however which way you want. You could use boot from volume, you could do regular sender volumes. Normal consideration applies there, right? But if you note, even at the central site, the compute nodes are using local ephemeral storage, right? There's a limitation today that we're working around on the way the deployment configures the way Nova consumes storage, so we're working around that today with local storage. But as I said, at the central site, you could do boot from volume. So it would turn out, if you were Ceph-backed, it would turn out exactly like if you booted from Nova to Ceph, if you use sender boot from volume, you could use the same thing. At the distributed compute node sites, those are defined as availability zones, and you can have whatever number you need there, right? So, and each of those distributed compute node sites can be whatever size you deem necessary, right? So that's how we start to help address the scaling factor that we talked about earlier. You can start with 1 or 2 nodes and you can scale out, you can scale back, things like that. We're not being prescriptive about what type of hardware you're deploying there, right? So that can help play into the environmental concerns. You can put specific hardware out there that's tailored to fit that particular edge site. And for the manageability, it's still supported and deployed by the undercloud, right? So you're getting closer and closer to sort of a zero-touch provisioning where you have a node out there that somebody can go and replace or add nodes, and you can import those nodes into your management system, undercloud in this case, and you can deploy OpenStack compute node functions to them. So we're getting closer and closer to being able to do those sorts of things, and this is how we do it. Now we're going to drill down just a little bit more. We're going to talk about, what I talked about is deploy with OOO, right? So no special sauce there. It's using Director. The undercloud resides in one place per cloud or per cluster. You may have more than one cloud, right? In this case, though, there's one that we're displaying and it exists at the primary site. So that's kind of, that's the way the design works. The container registry, so OSP 13, Queens, is container-based. The OpenStack services are running in containers, and in this case, the container registry needs to be back at the central site. Now you'll notice on this slide I penciled in satellite, because it's a great tool for managing content. It has a lot of other functions, but my favorite function that's near and dear to my heart for these sorts of deployments is RPM management and container image management, and the way they tie into life cycles. You can consume that through your development, testing, QA, staging, production environments, and each of those can be tagged with specific life cycles to help you manage packages and container images in a manner where you can trust and you've tested those configurations and integrations that you've done to the product. So with something like satellite, it's a single system. I like to deploy it as a single system for an entire enterprise, but it may have more than one component. You may roll in capsules, right, for specific sites, depending on your needs. So even though it's one big system, it may be more than one server. And it's a big win for tying it. Our documentation talks about using satellite for the image management, and it details how to do that, even tying it to lifecycle environments today. So those are some improvements we made in the documentation that really are kind of helpful. Moving on, it's a single deployment stack, right? So you're going to run your deploy command one time, basically, and you're going to get one over cloud or whatever you've named your cloud deployed from it. Now, again, you can still scale it up, you can scale it back, you can do all the things that you could do today, but now you have the ability to manage edge sites as well. But an operation affects the entire stack, right? So when you're running an update to scale out edge 1, that update is running from your central site, and your director is doing and touching all of your nodes consistent with the regular deployment or update process today. So that operation is focused and targeted on your edge site that you're scaling out, but every node will participate at least to some degree in that activity because of the single stack nature of the way that it's working today. Okay, so sites are defined by availability zones, so nothing new, probably no surprises there. Your distributed compute node sites are going to be an availability zone. You can have more than one availability zone per edge site if you needed to, but that's not what we're seeing today. Generally, the edge sites are kind of lumped in as each to their own availability zone. VMs are deployed to a specific location by scheduling to the desired availability zone. You could do more than one in your, more than one operation, and you can populate your VNFs to your edge site as you need to be able to do. We talked about the primary site, and it can also contain compute nodes. So you may have an availability zone there that has your primary site. And again, all distributed compute node sites and the central site, the compute nodes use ephemeral storage in this case, right? So they're using the local storage on the compute node. The primary site can have a compute role that uses sender volumes like I talked about, and that could be backed by Ceph or whatever your sender volume storage provider is, okay? And one thing to note is that each site is now its own role, right? So when you consider composable roles and composable networks that we introduced a few versions ago, this kind of takes that to the whole new level, right? So each site is a role that is expanded from your primary compute role. So you might copy your primary compute role, rename it, and then tailor it so it uses the correct networks for that site. It has the right services for that site if there's some sort of changes that you would do, and these sorts of things. So it adds a little bit to the complexity of your deployment templates, because each site's going to be a specific role. We've always had the need to deploy different roles for things like different hardware, right? The different network or NIC configuration. And now these are compounded by the need for each site or distributed compute node site to have its own role. So you may, in fact, have more than one role per distributed compute node site as you scale this out over time. If your hardware changes and you need to introduce different values for your CPU pin sets or your huge pages and things like that. So just something to note. And it's once you get the hang of it, it's pretty straightforward, but it is something that has to be done that way. Distributed compute nodes is only available today for the compute service. The edge cloud applications will need to be designed to consider their own data availability, locality awareness, replication mechanisms. In addition, live migration is not available in this particular release, right? Compute nodes at the primary site, once again, still using the local ephemeral storage. Now, that doesn't mean your VNF vendor can't be tailored to use a local storage at each site. It just means OpenStack's not providing it in this release. Okay, so if you had an NFS server or iSCSI server, something like that at your edge sites, and your VNF vendor could use it, that's totally fine. It doesn't really impact your architecture. It just says that we're not providing it in the initial release of this, although there's some work upstream that's going to change that over time. Also, with regard to storage, if you're Ceph-backed, remember that Glance uses Ceph, right? And typically when we talk about Ceph, we talk about raw images. They take a little bit longer to upload, but based on the Ceph mechanism for its copy on write technology, they're very quick to deploy and snapshot and things like that. This changes that mechanism. We're using local storage on the computes. So we want to go back to using QCOW images for those because they work best with libvirt, right? And so just something to think about as you design and architect your deployment. If you're going to use any Cinder boot from volume, those still want to be raw because Cinder is managing and presenting the disk as network attached for you. But if you're using local ephemeral, and it's just a regular Nova boot, so to speak, then those should be QCOW images, or QCOW2 images. Let's talk a little bit about networking. So typically what we see in the infrastructure side is L3 routed topology. This is what we're recommending, this is what we're seeing a lot of, and that's where I'm talking about the different roles coming into play so that each edge knows what networks it needs to use and how to ask for those networks from OOO. For workloads, we're talking about continuing to use provider networks. And if you look at our documentation and the little note here, we're talking about stretching provider networks to where they need to be. So they start at your controllers, and they may be needed at edge site 1, edge site 5, and edge site 7, and that would share a provider network. And you use them just like you do today. But of course, then you've got underneath, you've got a complex tunnel mesh kind of thing to facilitate that's handled outside of OpenStack today. But from OpenStack's perspective, you can tell it to deploy, and you can tell it to use that network, and you can tell the VMs to go to those availability zones, and the network's already there for it, right? So very similar to what you would do in a top of rack switch configuration. The computes that need to use that provider network need to be attached to it. That's still the same case, but now we're talking about mechanisms for distributing that over a greater distance, and so we have that kind of functionality to consider. Since we're talking about NFVi, we still want to talk about optimizing for network performance, and these are the same solutions that we look at today. SRIOV, right? So passing virtual functions into virtual machines. OVS DPDK, where we use OVS DPDK and pull mode drivers on each hypervisor to facilitate fast packet processing to get them from the wire up into the VM, right? And OVS offload, which is in tech preview today, which uses a combination of SRIOV-like functionality and OVS functionality to plumb those virtual functions into virtual machines and offload the packet processing where possible to the network card. That's a tech preview function today, but there are several vendors that are working with Red Hat to kind of to bring that farther and farther along. And then there's a note at the bottom about routed provider networks, right? So I talked about in bullet 2 about provider networks, where you have to kind of stretch a network to go from one place to another, and it's basically one big flat provider network across different sites. Routed provider networks might allow you to do that a little bit differently, where you have one network, and then you define segments for each network. Edge segment 1, edge segment 2, your leaf 0 or your control plane segment can all be defined with their own VLAN or their own segmentation mechanism, their own segmentation ID, and then they can present different subnets, right? So now, I think I have a slide for this. If I do something like that, I can define a network and I can put it on VLAN 1, 2, 3, right? And I can say, well, I want that network to be a /20. And I'm going to consume it for my controllers in leaf 0 and my edge 1 and my edge 2 sites. And when I tell OpenStack, with that model, when I tell OpenStack to deploy a virtual machine into Edge 1, it knows automatically to assign network space out of the 114 network. So now 10.10.120/20 doesn't need to be extended or stretched to all these sites, but instead I could use the routed mechanisms that we want to use to get virtual machines assigned to the right network in Edge 1 and Edge 2. And in this case, the controllers are participating where necessary for DHCP and metadata services if necessary. And that I'll touch on a little bit farther along. Actually, no. Sorry. So I'm not sure where I buried this part of the slide, but the key thing there is there's really two mechanisms for assigning IP space, right? For getting the node an IP address it can use, right? And so if we talk about a stretched VLAN, it works just like it always had. It's flat. The networks are going to broadcast back to the controllers. They're going to answer with the same DHCP and metadata agents that work today. If you do the routed provider network model, though, that kind of breaks down, right? Now you can introduce DHCP functions in your switch to forward that traffic, to back to your controllers. And that's one way to do it. And you can also use config drive. If you use config drive and you set up your networks to not do DHCP, then config drive will pick up the work step of assigning the addresses to the node for you. So not only will it provide the metadata service like it always has, but it'll provide the address for you as well. And it'll be configured as a static address on that. So you won't have to keep looking back or running DHCP or have that dependency on DHCP for it to keep its address. But if you use DHCP forwarders, because in reality, not everybody's going to support config drive, right? Or support cloud init even. If you don't have cloud init, maybe you're running some sort of virtual network function that is a router, and it's the actual server. It's been ported right into a virtual machine, and it's not typical Linux. It has no support for config drive, right? So then DHCP forwarders can be used, and you can go forward that traffic back to leaf 0, get your IP address, and then continue forward with your configuration that's going to be handled by your VNF orchestration itself, right? So a little bit of separate functionality there. But both cases are you have the ability to do it both ways. It's just easier if you have cloud init support. You can just turn on config drive and it kind of works out of the box.
Thanks, Brian.
Mm-hmm.
All right, we have 7 minutes left. And I'll leave a few minutes for the questions. But what we talked about is available today. It is covering majority of the use cases, I would say. However, it's not covering all of them, and there is always room for improvement. So what is the ongoing upstream work where we are being involved and what we are trying to improve for the coming releases? One of those improvements is deployment of each site as an independent stack. You saw what Brent was presenting. We have one deployment stack, which is doing the whole deployment. What we are doing, we are working within OOO to break this deployment into multiple stacks and having each site being deployed as a single stack. This improves resiliency, this improves scale, so that if one of the sites you want to update, you can update one single stack rather than running through the whole environment and making sure, because the procedure, the operation will run through the whole stack, and it will make sure that all the nodes are in the same configuration, are in the same state. So this will be a little bit improved, and that's work under OOO. There is a work to introduce the storage deployment at the edge, the persistent storage, and that needs multiple improvements in multiple projects. One of them is to be able to deploy and assign different storage backends per Nova instance, so that you can define this site has this storage backend, site B has a different storage backend. So that's one of the things. Another thing is to deploy multiple Ceph clusters through OOO. So that's another thing, since you want to have really dedicated cluster to your remote site, therefore you need to deploy multiple clusters. So that's another ongoing work. And with the combination of assigning different backends, you would be able to assign one Ceph cluster to remote site 1 and second Ceph cluster to remote site 2. There are improvements in way of reducing the footprint. So if you want to deploy the storage and compute at the same site, you would be able to hyperconverge those into one single hardware. So that's going to limit the footprint, which we discuss as one of the requirements and challenges. Increase of scale is very important. We said that we are deploying hundreds of thousands of sites, and we are definitely reaching some limitations from the deployment perspective, but also from the OpenStack perspective. So there is ongoing work of applying Cells v2, for example, for improving the scale limitations at OpenStack. There are improvements in Triplo project. There are other improvements in other OpenStack projects which we are working on. And one more for distributed DHCP and metadata agents for improving the resiliency if the network connection drops out, to provide a little bit better availability for the services at the edge. Where can you learn more? So a lot of those things are being discussed at the OpenStack Edge community computing group. There are use cases which are gathered across the industries, not necessarily only telco, but also enterprise use cases. You can list through those. There are reference models and architectures defined by the Edge computing group, which the distributed compute nodes is also inspired by. You can join through IRC Edge computing group. You can join the mailing list, and you can definitely also join our meetings, and you see the schedule of the meetings themselves. With that, we have something like 4 minutes, so if you have some questions, definitely go for it.
So your title of the talk is NFVi, right? I didn't see anything about NFV. So if I have a service instance running at my edge site, at the core site, and I have multiple networks which are running on any of the one edge site or across multiple edge sites, how do I do service chaining across them?
So right now, service chaining would require integration with a third-party SDN, right? So we don't have built-in service chaining functionality right now.
So we can use like tungsten fabric or something?
Yes, absolutely. You could use the tungsten fabric, something like that.
And another thing is, you're saying routed L3 networks
Right.
between the edges and,
Yes.
and the core. What is running underneath? Who's configuring all those tunnels? Do we have any IPsec? Is there any privacy, any security?
So today, the way that it works is those are just VLANs located at each site that's configured on the local switch and router hardware, right? And so the compute nodes just talk out their default gateway, the virtual machines on the compute nodes talk out their default gateway like they normally do. You still have the ability to use OpenStack security groups and all that kind of functionality where you can. However, some of the SRIOV and other technologies limit that functionality, right? Because you're actually passing the whole virtual function through to the VM. There's nothing to do an IP tables match on the host, so you don't get but that's a limitation of the technology. With OVS DPDK, you still have some limitations as well around security groups. But they're working on on improving those.
So on the edge side, you said I have minimum amount of IT intervention and have it as much automated as possible.
Right.
That's what you said. And then you're saying SRIOV workloads. SRIOV workloads require a lot of static configuration where somebody like IT has to go configure it. Why even go SIOV route? You have other fast performance packet paths. So why even go with SRIOV?
So at some point, you're going to run out of resources on the compute node, right? So if you go with DPDK, you've got OVS DPDK, you've got to take compute resources, CPUs, and dedicate them to that functionality. Also, each of your virtual machines, your virtual network functions, are going to have DPDK running inside. So they're going to be consuming entire cores for those sorts of operations, right? So SRIOV is still a player out there because it eliminates the need to dedicate additional compute, CPU resources at the network function.
So what if you use SmartNIC with
Right.
the virtual router offload?
Right. So as that technology continues to come, today it only supports a few pieces of OVS offload, not the entire stack. But we do offer it today in Tech Preview. It does things like, and it is a big help with that. So now you get the fast functionality, you get the OVS functionality, and you don't have to dedicate additional CPU resources. So we're big fans of that, but it's a little bit early days yet. I think this year we'll start to see that mature a little bit more. And in our OSP 16 product, our next full-featured, long life release, you'll see a lot more integration with the RHEL 8 and other kinds of things.
I think Tungsten Fabric gives you answers to all of these things.
But
Perhaps you want to look at that.
Tungsten Fabric does
Tungsten
consume.
Fabric employee. Real quick, there's a session from AT&T today on remotely configuring SRIOV.
Yes.
So please.
Thank you. All right, we ran out of time. Thank you very much. If you have any further questions, please, you can come here and we are happy to discuss further.